So the first question is, calcium hydroxide is used to neutralize acid spills. Now, why would calcium hydroxide be a good choice for that? It's a base. Above calcium hydroxide, write the word base. Now, all acids and bases produce a salt and a water, which is, if you look at this chemical reaction, that's what it's going to do. Reacts with hydrochloric acid according to the following equation. So, I've got, matter of fact, give me just 1 second. Let me do this real quick. Let me pause. To be put up, you don't need those out. Alright, so here we go. So this one I just make a little bit bigger so I have more room to write. So I have CaOH2 plus HCl yields CaCl2 plus H2O. Now, to do all stoichiometry problems, what do you have to have? Balance. Take just 1 second and see if you can balance that equation real quick. Is that what you got? 1, 2, 1, 2? Okay, very good. Then it gives you that. So if you have spilled 5.4 moles, okay, so it says 5.4 moles of HCl. So that's how much you accidentally knocked over. Now that's quite a bit of acids. I mean, that's almost like that's a bottle. So you're looking at a lot right there. And only put 4.8 moles of calcium hydroxide on there. Now, based on the numbers that we used, and you see, would you think that all of the acid would be neutralized? Just solely based on the numbers? No, why not? Because the base is less than the acid. But can you just compare those two numbers as they are? No, we've got to find something. What do we got to find? We've got to find the limiting reactant. Guys, I'm going to give you a little secret hint today. If and only if the question is, by the way, you may want a sheet of paper because all this isn't going to fit on this. You really may want paper because I know it won't all fit on that. If the question is, yes, ma'am. No. You want to? So, if the question is blatantly and only blatantly, what is the LR? Now let's look at our question on part A. If you have spilled 5.4 moles of HCl with 4.8 moles of calcium hydroxide on it, which substance is the limiting reactant? This is a shortcut. This is just something that just jumps out and says, hey, I am the limiting reactant. And you can do this. This is all you have to do, and it's just one step, very simple. Now, the reason this problem is going to be a little easier than the problem we're going to do in a few minutes is because what are the givens in? Moles. So what is the only thing you really have to do? All you got to do is divide by the coefficient. Guys, whatever you have here means nothing to the problem except it's identifying. It's just a way to mathematically prove something. I can teach you why this works, but there's no reason to. Just understand that it does work. Okay? So let's go back to this problem. And right here, we're going to start with, pen will work. We're going to start with 4.8 moles of CaOH2. And what is the coefficient on it? It's going to come right here. It's a 1. So nothing's going to change. So I have 4.8 moles of CaOH2. But then notice what happens here. We have 5.4 moles of HCl. And what is the coefficient? It's 2. Somebody help me out. What is, you with me? All I did was just, all right, so what is the number there? What's 5.4 divided by 2? 2.7. Now, have we just identified our limiting reactant? Yes. Who is it? That's it. That's all you have to do to identify. So that tells me that HCl is my limiting reactant. Now, by definition, what is a limiting reactant? It runs out first. So that's interesting. I started out with more moles of HCl, but did my less moles moles of calcium hydroxide clean up the spill? It sure did. Chemically speaking, why do you think that's true? What do you mean by bigger? Okay. What makes an acid an acid? And this is kind of a total side note, but what makes an acid an acid? Hydrogen. What makes a base for your definition today? Hydroxide. But so when we look at HCl and we look at CaOH, what I'm trying to do is, do you agree that when we make an acid and a base, we really just kind of get a water, or really we just get HOH? So it's neutralizing it, right? Isn't water trying to neutralize something? But why would I need less base? Okay, so for every one hydrogen in hydrochloric acid, how many hydroxide do you have for calcium hydroxide? 2, so you have double the amount, right? So you just need half as much. Does that make sense? So you need half as much of this because everyone's going to neutralize, but you have 2 per molecule. So does that make sense chemistry-wise? You just need less. So technically speaking, wrong button, how much calcium hydroxide would I technically need to neutralize it all? 2.7 moles. That would be equal. There would be no limiting reaction. Everything, that's a perfect amount. Like if you're going to bake a cake, you have the perfect amount of ingredients to make it. So that's how that would work. So now we've identified our limiting reactants. So let's look at part B. This is the new part, and it's the last topic that I'm going to teach you. This is it. Everything else we've covered that's on the test on Wednesday, and this is the last one. Yeah, I'm going to start writing something. And there's only 2 steps. All right, so here are your steps. So the first thing that you have to do, number 1, is obviously, if the question is how much excess remains, well, you've got to find out which one is the excess reactant. That's an obvious statement. But then this is what you got to do. Once you've determined your LR and ER, you've got to convert your LR to your ER. And this is where students have the biggest problem. They stop at step 1 and say, that's how much remains. So let's give you an example. You start with a dozen eggs, you bake some cookies. Okay? You use 9 cookies. Is that how much remains? No. Excuse me, you use 9 eggs. My bad. You start with a dozen eggs, you use 9 eggs. Is that how much remains? No, that's how much was used. How do you find the remaining? You subtract, which is exactly what step 2 is. A lot of people forget that this is just like cooking or just like doing anything in the real world, but it's using moles and grams and chemical formulas. It's the same concept. You've got to remember, so when I take that acid and I accidentally spill it, when I pour some base on it, is that acid going to use up some of that base? Yes, but not all of it. So the goal is to find out how much of it do I have left over. So what you would have to do is you would have to convert the LR to ER to find out how much was used. And then once you know you're used, the question isn't how much was used. What was the question? How much remains? How much is left? So I've got to know how much I started with, which is the given. And I subtract from it how much was used, which you find from step 1, and that tells me how much was left. Does that make sense? So let's work through the problem. So what was the limiting reactant again? It was 5.4 moles. Oh, one more point I want to bring up. Down here at the bottom, and Callie kind of made a point of this. On the very, very far right in brown, it says the units must match. And what do I mean by that? Your given was in what? Moles. So your used also has to be in. So you can't have your unit in given in grams and subtract moles from it. Make sure your units match. Okay, I do want to bring that point out. That's common sense, but I just want to say it. So I have moles of HCl. Now, I need to get to NaOH, right? Because I'm converting from LR, and I need to get to my ER. Now, since I'm already in moles, what can I do? No, I don't need grams. Very good. I need to go to moles, not Na. I always write Na right there. It's CaOH2. Now, this is an easy step. Is this anything different from what we've ever done? What step is this? It's your mole to mole. What is your mole to mole top to bottom? It's 1/2, right? Yeah, it is 1/2. So this is going to be, is what, 2.7? Yeah, okay. So it's 2.7 moles of CaOH and OH2. And remember, this is how much was used, not remaining. The next part is just a simple subtraction. Now, am I in the correct unit? Yes. Okay. So, I started with minus, well, how much did I start with? No, of my excess. Very good, 4.8 moles. I used, so again, minus used was equal to what? Right there. 2.7, and remaining is how much? 2.1 moles of CaOH2. You agree that's not a difficult thing? It's what we've always done. It's just adding one more step to it. Let's do it. Say that one more time. You had to find the LR and the ER. You can't know how much excess remains if you don't know what the excess is. Does that make sense? It's kind of like if you're baking and you want to know what all you have left over, well, you got to know what you used up first. Make sense? What? Can't count a chemistry? Can you count moles? Nope, it's okay. And there's a process for everything. Everybody got this? So now that you've seen it once, let's actually work through each part a little bit quicker so you don't have to look at the rules and you don't have to write those down. So these next two are just going to be straight problems. There's no rules or anything. You've already got those. All right, so it says aluminum oxidizes according to the following equation. Al plus O2 yields Al2O3. And then it tells you that you have 0.098 moles of aluminum and you have 0.030 moles of oxygen. And then the question blatantly says, what is the limiting reactant? Now, since it blatantly says, what is the LR? Use that little cheat thing. Okay? first of all, what do you have to do to this? You got to balance it. Go ahead and balance it. See what you get. I need 3. I need a 2. So that means I need a 4 right there. So 4, 3, 2. Okay, 4, 3, 2. Now, if it blatantly says what is the LR, what was that little cheat? Very good. Moles over coefficient. All right, so let's start with aluminum. I have 0.098 moles of Al, all divided by what number? Y4. That's the coefficient. Somebody help me out with that number. Okay, and then the other one is 0.030 moles of O2 divided by what number? Y3. That's the coefficient. Very good. All right, so somebody help me out. That's just 0.01. All right, just from the blue numbers at the very top, can you automatically know that oxygen is the limiting reactant just because it's the least? No, do not assume that, because I'm guaranteeing you in a few problems you're going to notice that that's not true. You can't assume just because oxygen is the least that it's going to be the LR. There are some problems where that is not true. But in this case, is O2 the LR? How do you know? Because that value is the least, right? So that then tells me that this is my LR and this is my ER. Yes, ma'am. AL and O2. Remember, we use this just to identify. That's why I don't really put units there, because I'm just looking for a number value. Which number is the least tells me it's the limiting reactant. Does that help? All right, go ahead. In this case, the purple and orange numbers. And the purple and orange. That least is the limiting reactant. In the blue, the givens are not. Okay? All right, so then it says in B, how many moles of the excess reactant remain? So here's what we got to do. How do I find how much excess remains? What's step number 1? Very good. Convert LR to ER. So I got to go from LR and I got to go over here to ER. So our limiting reactant was 0.030 moles of O2. Now what's the good news about these two problems so far? It's just a straight mole to mole. There's no grams to worry about. And mole to aluminum. What is my mole to mole ratio top to bottom? 4 to 3. Very good. So, can anybody do that in your head? What is it? Sure. Very good. Now, what do we know about that? Is that how much is remaining? Very good. This is, again, my used value. Remember how I tell you every single year I see students making the exact same problems? I keep saying the repetitive parts of this because I see the same problems every year. This is the part where people just circle that and say, that's how much is remaining. You've got to remember, that is what is used. All right, so started with minus, so how much did I start with of aluminum? Okay, 0.098, right? Okay, I used 0.040 moles, and the part that was remaining is just a simple subtraction, which is what? 0.058 moles of Al. And so that's how much I would have left. So if I found some more oxygen, could I keep reacting? I sure should. Sure could. Okay, because I got a little bit of oxygen left over. I sure should. Any questions? See if you can do number 3 by yourself. It's very similar. The only thing that's different is the reaction. I'll tell you this. First period had some trouble balancing this, so I will help you balance it. ZNS plus O2 yields ZNO plus SO2. And here's what they figured out is that the oxygen on both sides kind of messed it all up. So here's what you got to do. You got to put a 2 in front of both of these, which gives me how many total oxygens on the right side? 6. Well, can I make 6 on the left? What do I need to do? A 3, and then what else do I need? And 2 in front of ZNS, so it's 23, 22. Okay? Alright, so see if you can go from there. See if you can do the whole entire thing. Alright, so here's the question. It says, if 1.82 moles of zinc sulfide is heated in the presence of 3.94 moles of O2, which is the limiting reactant? So remember that little cheat? LR is equal to moles divided by the coefficient. Alright, so I've got 1.82 moles of ZNS divided by what? 2. And then I've got 3.94 moles of O2 divided by 3. So what was my moles, or what was my number for zinc? Point what? Give me one more sig fig. 0.910. And then what about O2? 1.31. Alright, so this is just identified. So who's my LR? Zinc sulfide. So this is my LR. Oxygen is my ER. So it means I'm going to have some of that oxygen left over. Alright, everybody okay with that? Well, then let's move on to the second part, which is how many moles of excess remain. So I originally had 1.82 moles of ZNS, and I need to go to moles of ZNS to moles of O2. And what's the mole-to-mole ratio? 3/2, which gives me how many moles of O2? Okay, what is it? 2.337. Okay, 2.73 moles of O2. And remember, this is used. Okay, and so then it's just simple from there. It started with, again, notice I always do the same setup. Minus used. Tell you what, started with was how much? 3.94 moles. And then I used 2.73 moles. And it's all going to give me my remaining, which is 1.21 moles of O2. My bad. Pretty straightforward, right? Okay. All right. Now this next problem is going to shift gears, but it's nothing new. We've done every bit of it. It's just going to ask you for a little something different. So let's look at this next problem. Okay. Chlorine can replace bromine in bromide compounds. How do you know that that's even possible? Is chlorine above Br? Yes. Okay. Forming chloride compounds in the elemental bromine. The following equation is an example of this reaction. So it's got KBr plus Cl2 gives you KCl plus Br2. So I've got two questions for you. Number one, why does the Cl and Br, when they're by themselves, have the little 2's? They're diatomics, but why do they not have the 2's when they're with the K? Charges cancel. Very good. Very, very good. And then it says when 0.985 grams of Cl2 and 3.25 grams of KBr are mixed in a solution, which is the limiting reactant. So it says point blank, who is your LR, so we can use this little cheat. Moles divided by coefficients. But with this problem, it has one little challenge. You got to convert from grams to moles. It's a part of it. It's just what you have to end up doing, because most things are going to be given to you in grams most of the time in real life anyways. So I've got 3.25 grams of KBr. So all it is just one additional little step. So gram of KBr to mole, wow, I left the B out, to KBr. And then on the bottom one, I have to do 0.985 moles, excuse me, that's not moles, It's grams. Cl2, and I got to go from grams of Cl2 to moles of Cl2. And now I know the mass of Cl2 is 70.9. Does anybody know? Can somebody look up KBr? What is it? That's right. Remember that number from earlier. 119.0. Now, I'm going to let you write that down and then ask you a question. Is anything different than we've ever done before? Nope. It's just gram to mole conversion. Now, can you look at those blue numbers and automatically assume that Cl2 is going to be the limiting reactant because it's the least? Now, it's significantly less, right? So do you think it has a high chance of being the LR? Let's find out and see. All right, how many moles of KBr do I have? Let's know the answer. 3.25 divided by 119. Give me one more sig fig. 273. 273 moles of KBr. Let's do that. All right. And then what about my moles of Cl2? Okay. Moles of Cl2. Now, what can I do now to find my LR? Divide by the coefficients, right? So I'm going to divide here. I'm going to divide here. So what's that going to give me? Oh, I didn't even balance this thing. Wow, that was bad. 2, 1, 2, 1. Okay, so that makes a lot more sense. So I have to divide KBr by 2 and the bottom one by 1. So that gives me the same thing on the bottom, which is 0.0139. I know I'm cramming this in over here on the side. But what is 0.0237 divided by 2? 0.0137. So who is my LR? KBr. And that's an interesting concept. Look back at those blue numbers. We now know that KBr is our LR and Cl2 is our ER. But why is that strange? KBr was a lot bigger, right? So that tells me that I only need a little bit of Cl to react with a lot of KBr. Does that make sense? Okay, so now we've determined our limiting reactant. So now let's look at part B, and this is how it changes a little bit. How many grams of each product are formed? Now, let's pause for a second. How many products are being formed? 2 on that one. Let's just pick one. Let's go to BR, BR2. So scratch out where it says how many grams of each product, scratch out each product, and write BR2. We're just going to go to one of them. Makes it a little easier. But the problem is I've got 2 amounts. Which one do I pick? I need to pick the limiting reactant to go over here. Can you do that? What unit are you going from and to? You're going from grams to grams, right? Okay, you can use the moles. That's fine. So if that's actually a good point, Nick. If you want to use that number, you can use that number. Okay? So go from KBr to BR2. Y'all do that on your own. See what you come up with. You can pick either one. Which one? Alright, so here's what we did. So we can start right here and go gram to gram and just plug everything in and go. Now, the only part that I wanted your help on, what is the mole to mole, top to bottom? 1/2. So the problem that we have is make sure you do this right in your calculator. Okay? Again, I just want to kind of help you out, guys. Just one second. Okay? So if you do 3.25 times 119 divided by parenthesis, excuse me, I did that wrong. I put the wrong number in. 159.8 divided by parenthesis 119 times 2, close parenthesis, and hit equal. That will give you the exact final answer. Okay? If you'll just learn how to embrace that in your calculator, it makes things so much easier. Okay? So multiply the two top, divide, use parentheses, and then go. Okay? So what was the final answer to 3 sig figs? 2.18 grams of BR2. Now, Nick, did you start with moles? Okay. Let me show you this. Okay. Let me show you if just focus on this step right here. Okay, Tanaya, focus on that step that's in yellow. When I go back to this screen, is that not exactly what I just did right here? So I could have used that moles right there. Now, let me show you this. The reason you can't use this green number is because you just divided it by 2. Let's pretend that the coefficient of BR2 was 4. Then you'd have to do something else. Does that make sense? So that's why I really don't like using that, because I'm scared people are going to use the red circle versus the yellow. You have to do it prior to dividing by the coefficient. Okay, that's what scares me. That's why I say go back to the original and do it as the whole thing. Yes, it takes a little more writing, but you've already got the numbers, and just plug it in. Okay, any questions? Okay, all right, that's it for today. Yeah, my bad, I'm sorry. There you go. Any questions? Go ahead. Yeah, that's it for today. Huh? I mean, we'll go over one more sheet. The back, you'll do the back on Monday.